Coming up on Dr. Kiki's Science Hour, we're talking about finding supermassive black holes with Nicholas McConnell from UC Berkeley. That's up next on Dr. Kiki's Science Hour.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Dr. Kiki's Science Hour is provided by Cachefly at CACHEFLY.com.
This is Dr. Kiki's Science Hour with me, Dr. Kiki Sanford. Episode 123, recorded Thursday, December 8th, 2011. The biggest yet. This episode of Dr. Kiki's Science Hour is brought to you by Ford, featuring available voice-activated sync. Sync gives you versatile access to music, podcasts, and more from just about any device. Check it out in the new 2012 Ford Focus and at ford.com/technology. And by Netflix. Watch thousands of TV episodes and movies on your PC, Mac, iPad, iPhone, or TV instantly. All streamed directly to you, saving you time, money, and hassle. For your free 30-day trial, go to netflix.com/twit. Welcome, everyone, to Dr. Kiki's Science Hour. I'm Dr. Kiki, and this is the 123rd episode, and I am very, very happy to say that we are going to be digging into science once again. You know and love this show because it focuses in on one subject in the sciences for an entire hour with one expert, sometimes two, but we focus in on subjects for an hour with an expert. How often do you get that? So I hope you are ready to dig in today, ready to get dirty in this subject, because we are going to get into the topic of the hardest to see objects in the universe. Black holes, with Nicholas Wade from UC Berkeley. But before we get into that, I have the science headlines. So, 515-million-year-old Anomalocaris fossils were found in Australia. They're described in the journal Nature. The internal structure of the eyes found in these remains were well preserved, looked like the compound eyes of modern insects, and are estimated to have contained some 16,000 lenses each. Look that Cambrian organism in the eye. All 32,000 of them, if you can. Publishing in the Proceedings of the National Academy of Sciences, scientists have found more evidence of quantum mechanics in photosynthesis. Using laser light and chlorophyll antenna proteins, they found a mathematical link between coherence and energy fluctuations, which supports the hypothesis that incoming photons of light simultaneously explore every possible route for energy transfer within the molecule, ultimately deciding on the most efficient one. Voyager 1 is set to leave the solar system, and NASA says it is in a cosmic purgatory zone between our system and interstellar space. At 11 billion miles from the sun, the stagnation zone is characterized by an erratic solar wind, an increase in magnetic field strength, and an increase in energetic particles from outside the solar system. It's thought that Voyager 1 will enter the rest of the universe within a few months to years. Using the Spitzer Space Telescope, NASA confirmed the existence of an Earth-like planet within the Kepler-22 system, known as Kepler-22b. The planet's orbit takes 290 days and lies within the habitable zone of the very sun-like star Kepler-22. While no water has been actually detected on the planet, it should be able to exist on the balmy 72-degree Fahrenheit surface. Additionally, Kepler scientists announced 1,094 potential Earth-like planet candidates that they'll be looking into in the future. The Mars Opportunity rover discovered a material that looks like gypsum, otherwise called calcium sulfate, which precipitates from liquid water. If confirmed, it will be the most solid piece of evidence yet of liquid water on Mars's surface in the past, and significantly a less acidic water history. The rock was found on Cape York and is 1 to 2 centimeters wide and about 40 to 50 centimeters in length. Oh, and to tie this all up, bees butt heads to get rid of dissent within their colonies, and Large Hadron Collider researchers think they're going to find the Higgs next week. That does it for the science headlines this week. It's time to get on to the rest of the show. I'd like to thank our sponsor. This episode of Dr. Kiki's Science Hour is brought to you by Ford, featuring Available Sync. Sync's entertainment features enable you to access music and podcasts from most devices, including iPods, mobile phones, tablets, or flash drives. And with Sync, with My Ford Touch, you can play videos or display photos from your digital cameras or portable game device when your vehicle is in park. It's all made possible through a versatile media hub, which supports a convenient variety of devices for your music and entertainment, such as wired connections from just about any device through USB ports, SD slots, and RCA jacks, or wireless access via Bluetooth from Bluetooth-enabled devices. Just connect your devices and play. Once your device is connected, you can use Sync's voice activation feature to play what you want. Just a few simple voice commands are play genre, rock, play artist, and play track, whatever the song title is. Also available is Sync with My Ford Touch HD radio. This features iTunes tagging, which lets you tag a song you like on the radio, transfer the info to your iPod, and purchase the song directly from iTunes at a later time. Sync's versatile entertainment features are available in the 2012 Ford Focus. You can learn more about this and other technologies Ford is bringing to its vehicles at ford.com/technology. Into the show we go. Our guest today is Nicholas McConnell. He's a graduate student in astronomy at UC Berkeley, and he's completed his graduate degree at Boston University. And now he has been working on a project with the Gemini Observatory looking for black holes. And it was a big story this week because he is the lead author on a paper published reporting the largest black holes ever found. 2 of them, not just 1, but 2. Nicholas, thank you for joining me on the show.
Thanks for having me, Dr. Kiki.
You're welcome. So tell me about this study. What exactly happened? Explain what you did and the result. 2 big black holes.
Sure. Well, I'll start out with just a tiny bit of background. For a few decades now, astronomers have had a pretty clear idea that large galaxies have very large black holes at their centers. And over the last 10 or so years in particular, it's been sort of an ongoing arms race to try to find more of them using the latest and greatest technology with telescopes. But for a long time, the record holder, so to speak, had been a 6 or 7 billion solar mass black hole in a galaxy we call M87. And what my team was able to do was use some of the biggest telescopes from the ground, from the surface of planet Earth, and look at galaxies that were 6 or so times more distant than this M87 galaxy, galaxies that were in fact larger, and see if, because the galaxies were larger, they also had larger black holes. And so we report our first 2 measurements of this survey of galaxies, and in fact we did find black holes that were close to twice as large as the one at the center of M87.
Wow, so close to twice as large. Can you give us some perspective on exactly how big that is?
Sure. So usually when we talk about how big a black hole is, we compare the mass of the black hole to the mass of the sun. And in the case of these objects, these are about 10 billion times the mass of the sun in one case, and possibly as large as 20 billion times the mass of the sun in the second case.
Wow. How do you estimate the masses of something that you can't see?
That's a really good question. So we know that the gravity that an object exerts on other objects is directly proportional to the mass of the object. And so what we really do is we go about and we try to find signatures of the gravitational effects that these black holes have on surrounding things, such as gas. And in the case of our galaxies, actually we look at stars in the galaxy and see stars moving under the gravitational influence from the black hole. The analogy is we do the best we can to point something like a radar gun at these stars and measure how fast they're moving.
Wow. So let's get into a little bit more of the details of how that happens. What kind of, like, you're using the Gemini Observatory. What kind of tools are actually used?
Right. So the Gemini telescope is a giant telescope. Its primary mirror is about 25 feet across. And so we collect light from that, and the light goes into an instrument called a spectrograph, which breaks up the light into many, many different wavelengths of light. And once you have information of how bright something is at different wavelengths, you look for patterns, and you basically ask yourself, what wavelength does this pattern begin at, and what does it end at? And it turns out that the speed of an object causes the wavelength associated with a pattern to shift. If an object's moving towards you, it shifts to shorter wavelengths, and if an object's moving away from you, the light shifts to longer wavelengths.
Right, and so, is this like the red shift that
yes,
we talked about?
Yes, it's the same phenomenon. It's a red shift if it goes to longer wavelengths, and so that tells us that something's moving away from us. Mm-hmm. It's also, it's called the Doppler effect, and so Doppler radar that you hear about for weather is using a similar technique.
Okay.
In any case, looking at those patterns, the instrument allows us to look at the patterns in the wavelengths and therefore deduce what the speed of an object is.
Okay, so, and by getting the speed of the object, you're also, and you know about how far away the object is. How does that end up tying into the ultimate, this is how big it is?
Right. So if you were thinking about one object, there's actually a pretty simple algebraic equation that relates the speed of the object, the distance between the object and the mass that it's orbiting, and the actual value of the mass at the center. Mm-hmm. So as you said, we observe these patterns coming from different regions of the galaxy, so we can measure just based on the angle in the sky how far away the stars we're looking at are from the black hole, which we assume is at the very center of the galaxy. Mm-hmm. And so we know the distance based on the angles, and we know the speed based on the redshift that we measure. And so if it were a perfectly simple case, we would just plug it in algebraically and get an answer for the mass really easily.
But it's never that simple, is it?
It's never that simple. In our own galaxy, it's close to that simple, because in the Milky Way, if you look at the center with an infrared camera, you can actually see stars moving, and you can count the individual stars going around in circular or elliptical paths around the black hole. But the real challenge for these more distant galaxies is that instead of being able to pick one star from another star, all the light from the different stars gets blurred together. And so instead of looking at just one star and measuring its speed, what we really look at is the combined speeds of millions of stars at the same time.
Right.
And we end up using a lot of statistical analysis to actually get the black hole mass.
Okay. And so from that, you're inferring, based on all these stars and the millions of stars in the galaxy cluster that you're looking at, exactly how massive, what kind of mass would be necessary to get them moving.
That's right.
at that rate.
Yeah.
Yeah. Okay, so you've got these giant, super massive black hole. We know black holes, they grow by devouring other material. Once they start, they're going to, I guess, start accreting. They start getting more and more stuff into them. That's
right. Although I have to warn that the science fiction picture that a black hole sitting alone by itself is going to pull things from far away and consume them unstoppably, that they're vacuums that no one is ever safe from, is a bit of a falsehood. And so in truth, you need to direct material close enough to the black hole that it reaches the point of no return and is pulled in by the black hole's gravity without being able to maintain something like a circular orbit.
So let's stop for a second, and can we talk about the basics of kind of the simple picture of black hole physics? So
sure.
What is the event horizon, all that kind of stuff?
Right. So the black hole itself is an infinitely small, infinitely dense point of matter. It has a mass like the ones we've measured, but all of that mass is contained within a single infinitely small point. When we think about a black hole from the perspective of observing it and considering what it does to light, we use a radius that we call the event horizon. And again, the further you get away from a massive object, the less of a gravitational influence it has upon you. So if you're further than a certain distance, you can imagine being relatively safe from something's gravitational pull, such that if you moved away from it with a certain speed, you would be able to escape. But as you get closer and closer to an object, something like a black hole, then you have to move at a greater and greater speed to be able to escape its gravitational pull. And in the case of a black hole, there's a radius within which the fastest speed that we know exists in the universe, the speed of light, even that speed isn't fast enough to escape the black hole's gravity. So within that radius, everything, including light itself, is going to be trapped inside the black hole instead of escaping outwards. And that radius is what we refer to as the event horizon.
So I love this kind of physics or astronomy by inference. The fact that black holes can emit no light and that you can't see them using the telescopes that you use, even using infrared, anything. You're not at any spectra of light. You can't see them, and so you can only visualize them by the movement how they affect other objects.
Yeah, that's absolutely right. So when we look at the stars around a black hole, we're definitely looking at the stars that have managed to survive and we believe will continue to survive safely away from the event horizon of the black hole. In the case of distant galaxies where we see glowing gas near the very center, that also tells us that a black hole is there, but the gas isn't actually coming from the black hole itself. It's coming from just outside the event horizon, where the gas has heated to very high temperatures and is releasing tons and tons of light before it actually falls into the black hole.
Oh, that's interesting. Is there a name for that effect, or is it?
We usually refer to that as a quasar. If it's sufficiently bright enough.
Do you expect that there's always going to be a quasar associated with every black hole, or is that not supported yet?
We know for a fact that many black holes, including the ones we discovered this week, do not have quasars associated with them. The key ingredient, again, to make a quasar is to have gas that's going toward the black hole. You need to have something light up. And it turns out that basically due just to friction, as gas spirals into a denser and denser region toward the black hole, the individual gas particles rub up against each other and get much, much hotter. And as the gas gets very hot, it glows to outstanding temperatures and glows with brightness that rivals the brightness of all of the stars in that same galaxy.
Wow.
But you can't do that without gas. And so galaxies that have, by one way or another, been drained of their gas have quiet black holes that are not in any way considered quasars.
Right. So you have the active black holes that are actively sucking this gas in, and you can visualize the light that's being released due to the friction. But then you have also the quiescent black holes that are just lurking.
That's right. They're lurking. Fortunately, the bigger ones we know essentially sink to the centers of galaxies. So the notion that a black hole might be plowing randomly through our Milky Way and coming to swallow the solar system is a little bit far-fetched.
Right.
Even though they're lurking, we kind of know where to look for them.
It's good. It's good we have a few clues. I know that every once in a while, though, there's, we have ideas about supernovas. We have all these ideas about, star formation. Every once in a while, a study comes out, though, that's very surprising, that puts, new information out that wasn't predicted based on, the understood assumptions.
That's absolutely true.
Something that's really interesting also about these particular black holes, you mentioned the distance that you looked away. Why did you look? You looked even further than M87, where we have what was previously the largest supermassive black hole. You looked even further away. Why was that a factor?
It's a factor basically because the galaxies we're looking at are very rare. And so if you think about people, I'm sitting now on a campus, a university full of people, and I could say, how far do I have to walk before I encounter someone who's 50 years old? And the distance might not be very far. And then if I ask, how far do I have to walk to encounter someone who's 100 years old? I probably have to look a little bit further to find one of those rare people who's actually a centenarian. And if I'm looking for someone who's 120, then, I might walk a fraction of the planet Earth before I find someone like that.
Right.
Similarly, because we're looking for some of the rarest and most massive galaxies, we've been forced to look to greater distances just to get to some of them that exist.
And are they larger and more massive? Because we're looking back further in time as well. So, is there a factor of how long they've been around, making them more massive? The supermassive black holes, have they swallowed up lots more stuff? Have they had more time to grow?
It's not necessarily true that the supermassive black holes have had more time to grow. It's possible that in both small and large galaxies alike, black holes formed in all cases in the very early universe. But the environment of the galaxies might have something to do with it. Galaxies that grow up in dense environments where there's slightly more mass in the early universe are probably going to grow up near more neighboring galaxies. They'll be attracted by mutual gravity, maybe more strongly to these other galaxies. And so the real distinction that we think exists between the very large galaxies we see today and less massive galaxies is that the large ones have probably had opportunities to merge with a lot more other galaxies over time. A galaxy is generally the product of many, many collisions between smaller objects.
Right.
And if you're in a neighborhood where there's more collisions, then you're going to end up being bigger at the end.
In terms of the galaxies that you're looking at, these distant clusters, and the supermassive black holes that you found, is there anything that you can infer about black hole that you could infer about a black hole formation, or does it tell you anything about when and where and how things came about?
We're definitely not all the way there toward painting a clear picture of black hole formation, but I think this is a good step forward toward that. One of the simple questions that we don't know about is when these first black holes formed early in the universe, just how big were they to begin with? There's a couple different ideas about how they may have formed. And in one scenario where they formed from very massive individual stars in the early universe, we think that the first black holes may have been 100 or 1,000 times the mass of our sun, and would have then had to grow a factor of 10 billion divided by 1,000 to get their present masses. There's another scenario that some astronomers support where instead of a star, you have a cloud of gas that has the mass of many, many stars, and that in some special cases, that gas cloud can collapse directly into a black hole. And we think those black holes might be able to be a little bit bigger. They might start out at 10,000 or even 100,000 times the mass of the sun, and so would have to grow less over time to reach the masses that we observe today. There are a lot of in-between steps that are necessary to really understand which of those two so-called seed black holes are more likely. But measuring ones that have 10 billion solar masses today surely will give some extra information to help that eventual study.
Yeah, and going the science fiction route, the Large Hadron Collider, which might have produced microscopic black holes, but people who wanted that to be the end of the world, likelihood of microscopic Large Hadron Collider producing microscopic black holes and being the start of black holes. That's probably not the seed event you're talking about here.
No, those hypothetical black holes would have been much, much smaller than the ones that we think actually were created in the early universe.
Right. And when we're talking about the creation of a black hole, the microscopic, these hypothetical microscopic black holes, part of the existence of them is the fact that they're there for the blink of an eye because they don't have enough mass to actually maintain themselves. So is there some aspect of having a certain amount of mass be necessary for maintenance of a black hole?
Well, what I believe you're probably referring to is the fact that black holes over time can evaporate. And essentially, black holes spit out subatomic particles. And so these particles have extremely tiny masses. And if you start out with a tiny black hole, then it's possible that it doesn't take very long for it to evaporate all of its mass away in the form of subatomic particles. But once you get to something, a few times the mass of the sun, or even if you imagine like a person-sized black hole, those masses are large enough that it would take an incredibly long amount of time to bleed away all of the mass by emitting individual subatomic particles.
Right. But a person-sized black hole would not be something that would have enough mass to influence movement, and probably wouldn't be big enough to draw things toward it.
No, just as a person's mass in the form of a person isn't enough to draw things to it. If that person were compressed into a black hole, the mass would have the same long-range gravitational effect as the original person.
Yeah. I need to take a quick break for another word from a sponsor, so just hold on there for a second, Nicholas.
Sure.
Everyone out there, this episode of Dr. Kiki's Science Hour is brought to you by Netflix. Netflix streams thousands of TV episodes and movies directly to you instantly, which means that you save time, money, and hassle, which we all like. There are several easy ways to instantly access streaming movies and TV shows with Netflix. You can watch Netflix movies and TV shows on your Mac, PC, iPad. There's an iPad app, your iPhone, and some Android devices as well. And if you're a gamer, you can use your Xbox 360, PS3, or Nintendo Wii and watch Netflix right on your television. Additionally, you can use a set-top box like the Roku box or Apple TV, which are cheap options and easy options to be able to access Netflix programming. With Netflix, you can watch movies and TV shows instantly using any of these devices, and you can begin watching on one device, stop wherever you need to take a break, and then if you want to pick it up someplace else, say you started watching it on your TV using a Roku box, stop the show because you had to leave, get on the bus, you've got your iPhone, you can start watching where you left off without any breaks in the service. Whichever way you choose, you can to access Netflix. You can watch as many movies and TV shows as you want, anytime you want, and you can cancel at any time. So go to netflix.com/twit for your free 30-day trial. Be sure to use this URL when you sign up for your free trial, netflix.com/twit. We thank Netflix for their support of Twit, and we hope that you enjoy watching TV and movies instantly with Netflix. Back to the show. I'm not watching Netflix. I am watching a screen here, my monitor, but I'm talking with Nicholas McConnell from UC Berkeley. He is in the astronomy program there as a graduate student and has just published a paper on finding the two most supermassive black holes in the universe so far. So to get back to our conversation, the supermassive black holes that you found, they're very distant in our universe. Are they in the same area of space? Were the areas of space fairly disparate that you chose to look?
It's interesting. They're actually relatively close to each other in terms of the overall night sky. In fact, each of them is a giant galaxy in the center of two different galaxy clusters. But the two clusters appear to be combined into sort of a supercluster of galaxies. And so not because they were a supercluster, but because it so happened that two of the largest and most easily observable galaxies in the night sky were in different locations of this supercluster. That's where we ended up starting our investigation.
So there's a possibility, since you're looking in this one area, is there a possibility that there are many more massive, supermassive black holes lurking out there?
Well, I would say that even though these are rare galaxies, the universe is full of a tremendous number of galaxies, and so there are a tremendous number of galaxies that, rare as they are of similar masses to these. And if you believe the general idea that the most massive galaxies should have the most massive black holes, then there are a lot of other candidate galaxies which may have equally massive black holes, or possibly also have exceptionally large black holes that would beat even the ones we discovered.
In terms of the size of the galaxies you were looking for, these supercluster, the clusters within the superclusters, how are there more larger galaxy clusters? I mean, you were talking earlier about, a centenarian, or if you're looking for a 120-year-old, we have a limit on, how old we get at current, with current science. And there is a limit on, how far we can look in the universe. But how far were you looking?
Well, to give you an exact number, we were looking about 300 million light years away, which sounds very far, but actually, in terms of the overall size of the universe, that's still sort of in our own backyard.
Yeah, it's close.
Yeah. Whether structures get bigger and bigger, the question is sort of a competition between things like galaxies and galaxy clusters and even superclusters of galaxies are mutually attracted by the combined gravity of all of the objects in these clusters and superclusters.
Right.
And so over time, gravity is trying to pull these things together into more compact structures. At the same time, our universe is expanding. And so empty regions of space in the universe are trying to pull the individual galaxies and clusters and superclusters apart from one another. Right. And there's this balance between things trying to pull together and things trying to push apart. And at the present age of our universe, the balance has arranged itself such that the largest coherent structures we see in our universe are these galaxy superclusters of similar size to the ones loosely containing the two black holes.
Okay, and so everything will probably be about the same size then for looking for more of these structures. But in terms of distance, are you going to have to look further back? Or is 300 million years pretty much where it is? It's like, humans arrived on the scene at a certain date, but...
Right. As well, I mean, there's a relationship between distance and time in astronomy. So as we go further back in distance, we're both looking out to larger volumes of space where there are more objects within a volume that we could possibly sample. But we're also looking back in time. And so the further we go, we start seeing the universe as it was when it was younger and younger and younger. Again, because overall 300 million light years isn't that distance in terms of a universe scale, the galaxies that we've looked at so far are more or less representing the same age in our universe's history that we are today. They're more or less present-day galaxies, even though 300 million years seems like a long time delay. And actually, that distance is it's close to the limit that we can achieve in terms of what kinds of angular scales we're able to resolve with the best telescopes. If you go much further than that, the specific gravitational effect from a black hole sort of gets blended in with the gravitational effects from other things on larger spatial scales.
Oh, is there? This sounds like an interesting question about the limits of the technology that we have currently. Is there, are people working on, more advanced optics? Is it something that more advanced optics would be able to solve the same way that, we have, guide star technology to be able to, get rid of atmospheric blurring? Is there, are there technologies that people are working on currently?
So on the civilian side, I have no idea what the military is working on, but,
right.
But on the civilian side, people are working to improve this adaptive optics guide star technology that you just referred to. So we should be able to use it better and more effectively in the future. The main development that's coming up in the next 10 years or so, hopefully, is that we're going to move from telescopes that are about 8 or 10 meters, 25, 30 feet across, to telescopes that are about 3 times larger. And if you have a telescope that's 3 times larger, it means that you can collect 9 times as much light for a given amount of time that you expose your camera. So you can see fainter things, which is good for looking to larger distances. And it means that the angles that you can resolve, again with help from this adaptive optics technology, are also about 3 times smaller. So if your limiting factor is what's the smallest angle that I'm able to detect, then a 3 times bigger telescope allows you to go 3 times further into the depths of the universe. And that's going to be a great start. We're really excited to use some of these large telescopes and get an even bigger sample of galaxies. But even 3 times the distance doesn't get us back to the early years when the universe was just originating. We're going to have to come up with some quantum leap forward, so to speak, in order to really directly survey black holes and galaxies that are still billions of light years away.
Yeah, it seems like especially if you're looking at visible light, this is a big limitation. But if you're looking at other energies, are there other energies that can give you insight into black holes? Say, radio transmission, or there's some pretty big radio telescopes, or can you look using some of the larger space telescopes that are out there? I mean, like the James Webb, they're planning on putting it out to replace Hubble in the next few years. Like, is there stuff that's going to advance that?
Well, James Webb is going to be a big advance when it launches for infrared light. Some of the radio telescopes, and we're building radio arrays on Earth that are getting bigger and better, help. And to answer your first question, can we use other wavelengths? Black holes, if they're accreting something, if there's gas around them, tend to release light at all sorts of different wavelengths. In fact, one of the best ways to detect a black hole that we otherwise didn't know about before is to use X-rays. X-ray space telescopes can find localized X-ray sources that are very often associated with black holes swallowing gas. And likewise, radio waves will do this, infrared light will do this. The James Webb Telescope is going to give us clearer and less contaminated infrared images than anything we've ever seen before. The telescope itself isn't actually bigger than the ground-based ones that we have in existence, but getting above the Earth's atmosphere will help a lot.
Right.
So these are all great things for detecting the presence of black holes, and they'll do wonders in that regard. But the problem is still the angular scale. If you want to measure a star that you know is close to the black hole, and only close to the black hole and isn't being influenced by other stars in the galaxy, then you need to resolve a very small angle. And that's a consideration that our technology is still, I think that we're going to see like a 3 to 5-fold improvement coming up in the next 10 years or so. But a 10 or even 100-fold improvement that we'd like to see to get back to really early cosmic times, we might have to wait for someone to come up with something really brilliant.
Right. But in the meantime, is it possible, I mean, we've got a black hole much closer to home in the Milky Way.
That's
so if
right.
you're not looking at the supermassive ones that are distant, there's probably a lot to be learned from black holes that are much closer to home.
Yeah, that's right. The black hole in our Milky Way is the topic of a lot of ongoing discovery. We pin down its mass more precisely every year that we look at it and see individual stars moving around it. It's actually sort of the one case where we've ruled out just about every single possible thing that it could be except for a literal general relativity interpretation of a black hole. There are other predictions of general relativity about things that happen to orbits only when they're around something as dense as a black hole and not in a normal regime that we'll start to be able to detect probably in the next 5 or 10 years. And other things that we're looking at from our own black hole in our galaxy are small flares of emission from either X-ray wavelengths or infrared wavelengths. We think that there are very small amounts of gas that are still trickling into the black hole at the center of our galaxy. And by having a really close-up perspective of what kinds of light that gas is giving off right before it falls in, we're getting a very detailed picture of how exactly one individual black hole feeds.
Is there any way, there's no information other than, the Hawking radiation that is emitted from the black hole itself. Is there any way that anybody's come up with, this is kind of sci-fi, but to actually visualize the singularity? Somebody in the chat room was like, well, if you have two black holes that are orbiting around each other, can you have the deformation of the event horizon give you some information about the singularity at the center of either one? Is there anything that people are talking about?
I would love to get that person in a room with some of my colleagues in the physics department here and see what ideas they can hash out about that. I'm not going to be able to say anything right now about a specific way that we could possibly view the structure of a black hole inside the event horizon.
Yeah.
My understanding is that once you're inside, your ability to transmit information outwards from it is severely limited. So I'm not sure if we have any great approaches to seeing the singularity. And frankly, a particle physicist might be able to say more about that than I can.
Right.
We can learn lots of other exotic things about black holes, such as how fast they're spinning, the way that before reaching the event horizon, they spiral in toward one another and eventually combine, releasing signatures called gravitational waves. These are things that, in spite of having detectors on the ground searching for them for many years now, we haven't detected any yet.
Yeah.
But we keep saying the detectors are getting better, and one of these days we're going to see some.
Yeah, that's the fingers crossed.
Yeah.
We really think they're there. We should be able to find them.
Well, I don't think we're at the point yet where we should have been able to find them, and we're disappointed that we haven't. I think
Right.
the next advance in that technology is going to really put our feet to the fire, where we better see them, or there's something seriously strange going on with our understanding of the universe.
Yeah, is the gravitational wave, is that something that's because you have these massive forces spiraling into each other, they just get shot off from the impact? Is that
I think it's a sort of a form of energy release. And so when you have charged particles like electrons or protons, and when you move those in a circle, they emit light. So they emit electromagnetic energy as a cause of their charges accelerating. And I think when you have massive particles and you accelerate massive particles, they emit energy via the gravitational force, which is gravitational waves. But on the level of fundamental forces, the gravitational force is so much weaker than the electromagnetic force that whereas we can detect electromagnetic radiation from across the universe, the gravitational waves that we would be able to detect require really, really massive and really, really dense objects, such as black holes or similarly compact objects, in order to get a strong enough signal in gravitational radiation that we can then detect it.
Right. As an astronomer, not a particle physicist, there's the interest that the particle physicists have of exactly what's happening inside the black holes and how all the particles are interacting and what makes them so small and dense and everything. But as an astronomer, what is it about black holes that interests you?
I think it's interesting is that black holes are sort of they're an ingredient in what makes up our universe overall. And in terms of the total amount of mass that in the universe that's contained in black holes, it's not a very large fraction. Certainly the amount of volume that they occupy is a very tiny fraction. But nonetheless, by doing things like heating up gas to really intense energies, emitting lots of light, they have a strange and really impressive power to exert influence on their surroundings by one way or another. That we haven't yet fully understood just how much of the way we see galaxies change over time is a result of activity in their black holes over time. So I sort of think about them as sort of one of the spices in the universe that you don't have to put in a whole lot of it, but it can have a profound effect on sort of the overall end product. Yeah. And it's possible that some of the ways galaxies we see have different shapes and colors is in some way influenced by activity on their black holes.
So understanding more about black holes could give us a better understanding of how they actually do, how they influence stuff.
Yeah, I think that it's an important thing to know to understand why in the universe today we see red galaxies and blue galaxies and disky galaxies and egg-shaped elliptical galaxies and galaxies that are forming stars still and galaxies that aren't forming stars anymore. There's so much diversity in galaxies in the universe today. And it's a really interesting question why we see that instead of all galaxies looking like the same thing. And I think black holes are part of that story, and it'll be interesting to figure out exactly what role they've been playing.
That sounds really fascinating. As far as your graduate research is going, are black holes the sole focus of what you're working on?
They've taken up, I mean, this has been a difficult project, so it's taken up a lot of my time so far.
Yeah.
But I have some other interests. The same data that allows you to measure how fast stars are moving actually tells you things about what sort of chemical composition the stars are made of. That can tell you how old the stars were, how long ago they formed, what sort of mixture of elements were in the gases they formed from. And those are other interesting questions about how do you form a galaxy? Do you form a galaxy out of pristine gas? Do you recycle the gas over and over to make it richer and richer in elements like iron and magnesium over time? And this information is in the same data. And so I think that in addition to working on black holes, it'll be interesting to see what other things we can learn about the stellar populations in different kinds of galaxies.
Yeah, it sounds that the element makeup. I mean, you're starting to get into the question of like, okay, you have a star that has particular elemental characteristics versus another galaxy with different stars, and why have those gotten in there? The black holes affecting it. You start getting a real picture of the forces, the events, what happened to actually make the universe what it is today.
Yeah. Yeah, and I think galaxies are really complicated things. There's all sorts of different processes going on. Every galaxy, to some degree, has its own individual story, and it's a challenge to take the individual stories of different galaxies and paint sort of more of a broader general picture to show how different kinds of galaxies evolve in common ways.
Right. That there is some, even though there is such diversity, there are commonalities in how things move over time, how they change. In terms of the study that you've come out with, the headlines that have come out, it's I've been looking at the stories that it's all over the news. It's Popular Science, Wired, Ars Technica. Just about everybody's covering it out in the web, the webosphere of science media, and there it's the big headline: 2 supermassive black holes. Is that the take-home message? Is that pretty much all that you think people need to go home with, or is there more to it?
I think anyone who takes home more than nothing is doing well in my book. But I'd say the other message is that on the one hand, these black holes are more massive than anything we've seen in our part of the universe, in our neighborhood, and that's a little bit of a surprise and certainly a fun result. In truth, we had evidence before that earlier in the universe, black holes this massive may have already existed. The measurements aren't nearly as precise as the ones we've done, but there was still some inkling that even 10 billion years ago, there were already black holes with about 10 billion times the mass of the sun. And we know about these because they were examples of quasars. We saw them based on the gas that they had accreted that was glowing very hot. But at some point, all of these galaxies with the very large black holes seem to have run out of gas. And so whereas we have a record of the presence of these objects in the very early universe, in the last 10 billion years, we sort of lost them. They must still exist, but we didn't know where they are or what was happening to them. So finding a couple black holes that are similarly massive here in our own backyard in a particular kind of galaxy tells us something about what the eventual fate might have been of these giant things that we saw so long ago in the universe.
That's really interesting. For you, the study of black holes, a lot of stuff gets into the science fiction-y side of things. People want to know if black holes contain wormholes. If they, we talked a little bit about this earlier. If they contain wormholes, are they a portal to parallel universes? As an astronomer studying black holes and looking up at the sky, are these questions that are, interesting to you? The tantalizing, sensationalist, sci-fi type questions, or do you look and just appreciate?
Well, I appreciate a lot, and I think that the science fiction questions are fun, and because we don't have access to the inside of a black hole, we don't directly have any observations about what happens once something crosses the event horizon. I'd say that a lot of those sci-fi ideas are still, in principle, on the table. There's nothing that's disproven them that I know of yet.
Yeah.
So it's great that people want to speculate about them. I think that's awesome, and maybe one day we'll figure out a way to determine whether these are actual possibilities or not. But I think the universe is remarkable and magnificent enough, just the things that we know about it as it is.
I absolutely agree. Okay, question, Doctor Who or Star Trek?
Oh, I am going to so severely disappoint you on this. I am actually not I haven't had much experience with either Doctor Who or Star Trek. Okay. Because I watched Star Trek 4, the movie, a long time ago, where I think they beamed up the humpback whales.
Right.
That's like one of my few experiences, so I'll go with Star Trek.
Okay. Doctor Who, Star Trek, the reason I was asking is because of their the worlds that they go to, the stars the solar systems that they visit, and the variety of planets. Looking at, I was thinking about your comment earlier about looking at the stars and the different elements that they have, and how, what kind of things you could infer about those neighborhoods, about those areas, and maybe, finding diamond planets, finding planets that are solid chunks of coal, or, there are all sorts of possibilities. And I think that some of these science fiction-y type stories, they hit on them a little bit. We don't know.
Yeah.
And we've seen possibly, I've seen the science. There's possibilities of diamond planets out there, right?
And I think if there's any lesson to be taken from the last few centuries of science, it's, you can talk about how something can't possibly happen, will never happen. There's no way we'll see an example of it happening until your neighbor down the hallway discovers it happening. So science fiction often eventually turns into science fact, and I think it's good to always be cognizant of that.
Yeah. But this time it wasn't somebody down the hallway. This time it was you discovering something. Congratulations on being first author on this paper and such a super massive discovery.
I'll let you get away with that one.
Thanks. But anyways, what's next for you? You're going to be finishing your graduate degree, and do you have any plans moving forward?
I'm waiting to hear where I'm going to end up. I assume I'll be doing astronomy research for a while more. I will finish my graduate degree next summer, and I think that a lot of the same work that I've been doing so far has potential to be pushed forward even further, and I'm sure I'll still be involved in it one way or another.
Good luck to you. I wish you very well, and thank you so much for sharing with us and talking about your discovery and about black holes in general, black hole science. It's been a fabulous hour.
Oh, well, thanks to you and to your listeners for being so excited about all of this.
Absolutely. All right, everybody, that does it for us here at Dr. Kiki's Science Hour. Many thanks to Nicholas McConnell. If you have any further questions about the discovery, you can always visit the websites, the organizations that were involved in this. You can go to astro.berkeley.edu for the UC Berkeley Astronomy Department, or you can go to gemini.edu for the Gemini Observatory, which was the home of the Gemini telescope that was used in this project. Additionally, McDonald Observatory was involved in this, which is as.utexas.edu/McDonald. And that does it for this week. I'm Dr. Kiki. This has been the Science Hour. And next week, we're going to be talking some neuroanthropology. That's right. Human culture change and brains and how they all fit together. So I hope you are interested and excited about next week's show. I know that I am. Anything to do with brains, Until then, you can follow my sciencey pursuits out in the interwebs. I'm Dr. Kiki on Twitter and my Facebook page. Additionally, Kiki Sanford on Google+. You can find me at drkiki.tv. Email me at drkiki@drkiki.tv if you have any questions, suggestions for interviews, or recommendations for videos for our science meditation of the week. I also like good sciencey music, so if you have recommendations there, let me know. And I think that's about it. So I will see you next week. Thanks for tuning in. Remember, all I ask for is 1 hour a week, and I do hope that it makes your world a whole lot more interesting. And now for your science meditation of the week.
What you're looking at here is a siphonophore. It's one of our favorite animals here at the Dunn Lab, particularly because of that question. A siphonophore moves and looks like one long animal, but if you look closer, you realize it's a colony of jellyfish, all attached to one long stem and swimming together, and each doing a separate job for the group. So is each piece on the siphonophore an individual, or is the whole colony the individual? It's sort of both. Here's Dr. Casey Dunn.
So instead of just being a single individual, they're colonial animals. They all grow from the same embryo just through a budding process, and they remain attached, and they share a circulation system But the really striking thing about siphonophores is that not all of the members of these colonies do the same things. So really, it's as if you were to continuously bud conjoined twins throughout your entire life. So whole bodies, except that some of these twins only fed, others of them only reproduced, others just had legs, and some were just giant hearts moving the blood for everybody. In our own bodies, clearly we function as individuals, but when you look at what we're made out of, we're made of a whole bunch of cells, and each of those cells is equivalent to cells that live on their own. So what is the individual in the human even? Is it the cell? Is it the body as a whole, or is it both? And what does this mean for the way that evolution acts on the structure?
This is Sophia Tintori from the Dunn Lab at Brown University in Providence, Rhode Island. Thanks for watching.
Web474 says, is there a black hole at the center of each universe? We don't know because we only have seen our own universe. And so far, we haven't seen the center of our universe. So that would be a really big black hole. So far, there are many galaxies that have black holes at their center. Is Nicholas still there?
Yeah, I'm here.
You're still there. Did I answer that okay?
Yeah, you basically answered that correctly.
All right, just making sure. I'm like, I see you on the screen. I'm like, you listening? Did I pass the test?